Talk about truth tables. This is section 11.2, truth tables. Okay, what truth tables are useful for is revealing the truth or falsehood of complex statements. Okay, so examples of things like complex statements are P and Q, P or P and Q implies R, all sorts of things we can cook up with these symbols, right? And the more things we put in there, the more complicated they are to parse and try to figure out what's going on. So what a truth table does is it will reveal to us which statements are true. So I'm going to make a big truth table with some of these statements here as an example of what a truth table is. So P and Q, P or Q, not P, P implies Q. Okay, so there's our basic skeleton for the truth table. And what we need to do is we need to run through all combinations of P and Q being true or false. And the way we do that usually is P is true, true, false, false. Q is true, false, true, false. That will be enough to give us all possible combinations of P and Q being true and false. Okay. So now let's fill out this blank here on the truth table. What goes here? Well, that is, we have to say whether P and Q is true or false. And the way we figure this out is we look at P's value and Q's value. P and Q are both true, so indeed P and Q will be true. So we put a true there in that part of the truth table. Now, if P is Q and true is false, are P and Q true? No. So this gets a F for a false. Okay? If P is false and Q is true, is P and Q true? No, it is not. So this also gets a false. If P and Q are both false, is P and Q true? No. It gets a false. Okay, so that's the truth outcome for P and Q. Now let's look at P or Q. This is an inclusive or. So if P is Q and true is Q, is either P or Q true? Certainly, right? Now, if P is true and Q is false, is P or Q true? Yeah, you only need at least one of them to be true. And then if P is false and Q is true, this is also true. The only way for P or Q to be false is if they are both false. So we put an F there. Okay, not P wants to know whether not P is true. This one's pretty easy. It's just the opposite of the column involving P. False, false, true, true. We don't care what Q's value is. We only care what P's value is for that one. And now if P, then Q. Okay, so if P, then Q, P implies Q, is true under what scenario? Okay, if P is Q and Q is true, is if P then Q true? Yes, yes. Okay. What if P is Q and true is false? Or Q is false? This is a no, right? If P then Q is supposed to hold, and if we have P, then we should have Q, but we don't have Q, so this is false. How about if P is false and Q is true? That's the tricky one. Okay? This is fine. Okay? This is actually fine. Okay? Let's think about this. So, okay, if I get paid today, then I'm going to the bar to have a beer. Now, if you see me in the bar having a beer, does that mean I have just been paid? No, right? If I have been paid, then I will go out to the bar to get a beer. But if you see me at a bar having a beer, that does not mean necessarily that I've been paid. It's possible for me to not have been paid and for me to have a beer at the bar. And that doesn't contradict the statement, if I get paid today, then I'm going to go have a beer at the bar. So that's why this statement is considered true in that situation. That is probably the trickiest one to remember. So you need to come up with an if-then statement that makes sense to you, that convinces you that P being false and Q being true is not a problem for if P then Q. Keegan.
Are there scenarios where it will be an issue, just depending on what the sentences they give us are?
No. Anytime you have an if P then Q statement and P is false but Q is still true, it's fine. It's totally fine. Okay, I mean, I'll try to think of another one. Okay, if the year is 2022, then the number of the year is even. Okay, if it's not 2022, the number of the year could still be even. It could be 2020 or 2024. So we would not consider the statement, if it's 2022, then the year number is even, to be false if it's not 2022 necessarily. We don't want to always have to say that. So this is the toughest one to remember. The last one, if P is false and Q is false, then we still have no problem with if P then Q. If P is false, then Q is obligated. So think about it this way. If P then Q, and P happens to be false, then there are no obligations on Q. Q can do anything. Does not matter. That's why the last two rows on this final column are true. Because if P is false, Q can do whatever it wants. Okay, it's only under the condition that P is Q that Q is also compelled to be true. That's why this is the only bad one for the implication. Okay, so let's do a more complicated truth table. Let's consider the following logical statement. Not P and not Q, or P. Okay, there's a statement. Not P, not the quantity P and not Q, or the quantity P. So this is going to be very hard to parse, and the way you deal with these complicated ones is you break them into their constituent parts, construct the truth tables for them, and then finally put it all together in the end. So we're going to make a truth table. We're going to look at P and not Q, because that's one of the things inside here. Then we'll look at not P and not Q, just so that we are looking at the right thing. And then we're going to take that thing, not P and not Q, or P, in the final column to finally get to what we want to find. And then, of course, I have true, true, false, false, true, false, true, false. Okay. So I'm just going to make my way from left to right in this truth table so that I can figure out what's going on with that extremely complicated statement, right? That complicated statement on the right would be almost impossible to put into an English sentence that we could parse, right? Even if you were to put that into a sentence that's grammatically correct and you said it to someone, they would just look at you with fish eyes and say, that doesn't make it, I don't know what you're saying. The only way to do this is to carefully proceed via this sort of situation. Okay, so we want to look at P and not Q. So this is an and, so we need both P to be true and Q to be false. The only way this is true is this second row. Right? Otherwise, these are false. Okay, are there any questions about that column? Does that column make sense? We need P and not Q. And only one of the four possibilities has P and not Q. Okay, now we're doing not the previous column. So all I do is I change all the trues to falses and all the falses to true. Okay. Now I have an or between this, which is this column, and this, which is this column. So I'm only looking at these last two these underlined columns to figure out what goes in my last column. I need either the green column to be true, or the blue column to be true, or both columns to be true. That's what I'm looking for. So this first one, I have both the green and the blue column to be true. So we're good. The second one, I have the blue column true, but the green column false. However, it's an or statement, so we're fine. The third one, I have the blue column false, but the green column happens to be true. So that's fine. And finally, in the last one, the blue column is false, but the green column is true. And so there. Okay. So there, look, the truth table has true, 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 true. So this statement is true no matter what the values of P and Q are. Anytime you get all trues in the truth table, there's a special name for that. It's called a tautology. It means something that is always true. Examples of tautologies include math professors are the benevolent gods among men. Right? It's always true. But okay, how could this always be true? Okay, well, if P is true and Q is true, then that or part on the P gives it away. Right? So these first two just happen to be true because P is true. Okay, let's look at the next one. We're just going to look at this row by row just to kind of convince ourselves this is true. Okay, if P is false, then I don't have the blue part. But, okay, if P is false and Q is true, I don't have the thing in the parentheses at all because P is false and Q is true. I have the opposite of that, but then I take the opposite of that and I get true. So, okay. And then lastly, I actually do not have P, but I have not Q. But since this is an and, I don't have this, and so when I negate it, I have it. Okay, so that it's very complicated. You wouldn't have thought that some statement like this would always be true just by looking at it. You really have to get down and do the truth tables in order to discover things like this. Okay. Questions? Keegan.
Do you always set the P and Q up of true, true, false, false, and true, false, true, false?
That's just the pattern that I use to remember it. It's probably the pattern you'll see in most textbooks. But if we have a third variable, then it gets a little more complicated. So how about we look at that so we can see the difference, right? Okay. Let's look at the following compound statement. P or Q and P or not R. So now we have P, Q, and R, which means our truth table, instead of having 4 rows, is going to have 8 rows. So it just gets a little more complicated. P, Q, R, P or Q, P or not R, and then finally what we're looking for, P or Q and P or not R. So P, I'm going to write true, 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 false, 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 false. You just have to find a pattern that makes this make sense, that we get all possibilities. Oops. So I like to go true, false, Okay, so now I get true, true, false, false, true, true, false, false. I think that'll take care of all possible possibilities. Nothing is repeated here. Okay. So right, there's two choices for each of P and Q. So 2 times 2 times 2 is 8. We know how to count many choices there should be. So there should be 8 rows, and indeed we have 8 rows here. And we have all possibilities for P, Q, and R accounted for here. So here, let's just go through this. Instead of going through this column by column, let's go through this row by row. I think it might be a little easier. P or Q, yeah, that's fine, because P, Q, and R are all true. P or not R, that's fine, because we have P. And then both of these, well, this last one is going to be true only in the case that the previous 2 columns are true. Now let's go to the next row. P or Q, sure. P or not R, sure, because we have P. And then once we have these 2 is true, we're good. Okay, P or Q, yep. P or not R, oh, we even have P and not R. So true. Okay, P or Q is good. P or not R, still good. And this is true. All right, now, R, okay, notice how the values of Q did not matter at all for anything that was going into this. This is because P is always true for the first 4 choices. All right? Okay, so now we're going to have P be false and Q be true. Well, then P or Q is true. P or not R actually this time is false, because we don't have P and we do have R. And since this last column is an and, we get false, because we don't have both of the previous columns. Okay, P or Q now is false. P or not R is also false, and this is false. P or Q now is true. P or not R is also true, and so this is true. And if they're all false, this is false, this is true, this is false. Okay, so in 5 of the combinations, this statement is true. In 3 of the different combinations, this statement is false. So when you have more variables, you have to add more rows to your truth table, right? Hopefully you won't ever see one where you have P, Q, R, and S, right? That sounds like, should that even be allowed? There's probably a law against that somewhere in the student handbook. Okay, let's look at a few more of these. Some important ones I want to look at here. P or Q and not P and Q. Okay, this compound statement of P or Q and not P and Q. Now, while we're drawing this table, think about what this means in English for a second before we fill in the table. And I'll come back and ask if you have any opinions. Any opinions about what this means before we get started? P or Q and not P and Q. Okay, let's take a look here. P or Q, this one's easy. If either of them are true, we're fine. So it's true, 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 false. P and Q is only true when we have both P and Q, but then we're taking the opposite of that. So we have false, true, true, true. That's the opposite of P and Q. Right? P and Q is true, false, false, false. So we take the opposite, false, true, true, true. Now in the last one, we're looking for both of the previous columns to be true. So we have false, true, true, false. This is sometimes called the exclusive OR. Remember, our OR, the basic logical OR, allows both things to be true. This one allows exactly one to be true. Okay, we can't, so, P or Q, but not P and Q. It's called an exclusive OR, and there's even a symbol for it, which you might see in the book for some homework problems, a circle with a plus in it. That means an exclusive OR. Oh, exactly one of the two things is to be true. Not neither and not both. And see, this is this part right there is exactly where one of them is true. And that's why those two rows are true. Okay? Now, I want to look at two compound statements. Not P and Q versus not P or not Q. And we'll see if we can get this done without going too deep into this truth table. Hope maybe we can figure this out without adding too many extra columns. So we'll see if we can get this done in one broad stroke. Okay, not P and Q. P and Q is true only in the first row of this column. Right? P and Q is true only in the first row. We're taking the negation of that. So this is false only in the first row and true otherwise. Okay. All right. Not P or not Q. Well, if they're both true, we don't have either of those. But for the other three possibilities, either not P is Q, not Q is not P is true, not Q is true, or they're both not true. So this is false, true, true, true. And you notice that these columns are the same. And so this means something called logical equivalence. If I could spell equivalence. Meaning that they are the same statement as far as logic is concerned. And in fact, this one is so famous that it's called one of De Morgan's laws. And we will meet this more next week. Okay? And the way that you write logical equivalence, according to this textbook, is as follows. We would say that not P and Q is double arrowed with P or not P or not Q. Okay, this is one of De Morgan's two laws. And in particular, what you're saying here is negating an and statement creates an or statement. And we'll also see that negating an or statement creates an and statement. Okay, the homework is going to be 6 through 30 even in this section 11.2. And that'll be due Monday.